Welcome back to our course on memory device technology for AI/ML computing. I'm your instructor, Dr. Shubhadeep from IIT Hyderabad. Let us try to recall what we were discussing the last time around. We began with an understanding of different phases of solids as characterized by range of order, with crystalline state having long range of order and amorphous state having the shortest range of order. We also saw that for the same material, the crystalline state has the lowest resistance and the amorphous state will have much higher resistance. And that is due to the scattering of the charge carriers which is involved in transport. This is also the main working principle of your modern day phase change memristor or phase change RAMs, as we saw from our energy landscape diagram. Try to recall our energy landscape diagram. When we have to go from the amorphous to the crystalline state, or the high resistance to state to the low resistance state, which is called the set, we need to give the system much less energy. The barrier is much smaller, but you have to wait for a longer time for atoms to go and find their minimum energy state, which is known as the crystalline state. However, when you go from the crystalline state to the amorphous state, which is your reset cycle, you need to give it a jolt. You need to give the system very large amount of energy, make it go to the melting temperature, very close to the melting temperature, where there is a lot of disorder in the system, and quench it back. Quickly drop back, remove the heat from the system so that the disordered state or the amorphous state gets kind of frozen. Okay, and also we saw how this is facilitated using Joule heating in PC RAMs by applying a very short pulse of very high amplitude to facilitate reset, which takes, as we discussed, the material above its melting temperature, and then suddenly you drop it also to have an effective quench. Whereas the set cycle is characterized by a pulse of medium amplitude but having very large time. So you give it enough time for your crystalline state to set in. Okay. So with this, we finished our basic understanding of the working principle of PC RAM. And today we are going to look at the technological aspects, starting with materials optimization. So as we know, the phase change material is the heart of any PC RAM, and it makes sense that we need to tune composition of the PC material so that you get ideal device characteristics. So as we had seen, that the so-called ideal material is something called GST 225. GST stands for germanium, antimony, and tellurium. And the ideal material had a composition of 2:2:5. And when people started making PC RAMs out of it, they saw that indeed the crystallization temperature is very low. The crystallization temperature being low seems like a good idea in terms of having lower energy to give to the system, but it will come at the problem of also lower retention or stability, right? Because any kind of thermal noise or thermal disturbance will be able to recrystallize this material. Okay, but what people surprisingly saw is that with low crystallization temperature GST 225, the reset current of the devices was also very high. Now, this is not what you would expect intuitively, but this is the case because when you have low crystallization temperature, recrystallization is very easy. Remember, recrystallization is you have already some amorphous state. Even a little bit of heat also can recrystallize the material at intermediary temperatures. So what you have to do when you do a reset is you do a very fast melt and you do a very fast quench. And to do a fast melt and fast quench, the amount of reset current you need to supply to the PC RAM or to the system needs to also be very large. And therefore, people decided in order to reduce the reset current, you need to play with the composition of this GST material. So the idea is, can we increase the crystallization temperature of this GST material? And the way to do that is to have a deep look at the so-called ternary phase diagram of GST. So as you can see from this diagram that I have presented in front of you, the ternary phase diagram of GST basically indicates what are the equilibrium phases and stable compositions that can be formed by mixing germanium, antimony and tellurium in different proportions or stoichiometry. Also, what you see is this so-called tie lines. The tie lines are nothing but they connect compositions that can coexist in equilibrium, meaning the material will phase separate into those phases under certain given favorable conditions. So these are your tie lines on which you try to find stable compositions which can give you your desired crystallization temperatures. So what people found out is, right in the middle of this equilateral triangle in between tellurium and germanium, so equal parts of tellurium and germanium, 2 and 2, and 1 part of antimony. So GST 212 has very nice properties when it comes to the crystallization temperature. By changing GST 225 in composition to GST 212, you can change the crystallization temperature to almost 100 degrees. You can increase the crystallization temperature from 150 to 253 degrees. And as a result, what happens is there is a drastic drop in the reset current because of the reason that we just explained. So 253 crystallization temperature means recrystallization barrier will also be very high. So you don't have to supply so much reset current and you don't need to quench it so quickly because the material is more stable even in the crystalline phase. As a result, you also improve the endurance and reliability because you are no longer affected by thermal noise. Okay. So, but one thing that you essentially see is that as you increase the crystallization temperature, the recrystallization time starts increasing also. So for GST 225, the recrystallization temperature was less than 80 to 50 nanoseconds. But now, because you increase the crystallization temperature, the set speed or set latency increased to around 80 nanoseconds. Okay. However, as we will discuss later on in our lecture, probably the last part of our lecture will show that the phase change RAMs have very niche applications such as in automotive embedded memory. And as you can imagine, in an automotive use case, you would want your crystallization temperatures to be even higher. Why? Because in automotive embedded memories, the PC RAM will be exposed to elevated temperatures. So you want higher TX for better reliability. And that people were able to achieve by incorporating other group 5 elements such as nitrogen along with having an excess of germanium. So as you can see, by playing all these tricks, by having excess germanium, you could increase it by another 50 degrees, and by incorporating nitrogen, you could go to almost 316 degrees. But just as we discussed earlier, all these improvements in retention by increasing the crystallization temperature, of course, as you can see, the retention improves, the reset current also becomes lower. But what is the trade-off? The trade-off is that the recrystallization time increases by almost 2 orders of magnitude, and therefore even the set latency, remember the latency is decided by the long set pulse, that also increases from less than 80 nanoseconds to almost 200 nanoseconds. So there is always a trade-off with trying to improve retention and reliability by increasing the crystallization temperature. Okay, with this understanding, let's start to look at or focus at the device design or the cell architecture. How do you design the cells so that you get very efficient switching characteristics? Now, this is guided by two key principles. So, the first principle is that you need to confine the programmable volume. Now, what is this programmable volume? The programmable volume of the PC RAM is the GST material, which will actually undergo the phase change from crystalline to amorphous back and forth. Why do we want to reduce the volume? Because more the amount of volume that you have to bring to melt temperature, more will be your reset current. So, as you can see over here, this is your top and bottom electrode, and this is your phase change material. So, the idea is, can we reduce the contact area between the top and the bottom electrode contacts such that the programmable volume also reduces? And as can be seen in this very nice illustrative graph, you have a clear correlation between the contact area and the reset current. As contact area reduces by orders of magnitude, even the reset current reduces by orders of magnitude, almost by a linear function. So the idea is, can we reduce the contact area where the PCM material will be programmed? And several device architectures were proposed to facilitate just that. Some of them I have shown over here. The first one is called edge contact, where the PCM material is just at the edge of the bottom electrode contact. And in the other two architectures, the mushroom and the confined, this is more like a vertical architecture. This is more lateral. These other two are more vertical, where the programmable volume is sandwiched vertically between the bottom electrode and the top electrode. And it actually turns out, in reality, if your only goal is to reduce the contact area, possibly edge contact method is much better. This is because to deposit this thin film of PCM is much easier than to lithographically pattern out the small bottom electrode contacts. And several research demonstrations have shown incredibly small reset currents, even going to 1 or 2 microamperes, by reducing the contact area drastically by using this edge contact method. You can go and search literature, lot of interesting papers, even using carbon nanotubes. However, as you can understand, the edge contact area will have problems in manufacturing yield, and therefore the common techniques of trying to make commercially viable products is your mushroom and confined cell architecture. And doing a comparison between the mushroom and the confined cell architecture may tempt you to believe that the confined architecture is better because it is the programmable volume looks even more constricted or even more constrained, because in the confined cell architecture, you kind of dig a small hole and fill PC RAM material, whereas here the PC RAM material is more exposed to the bottom electrode contact. So naively, one may believe, just from looking at lower contact volume, that confined cell architecture is a better architecture compared to the mushroom cell. However, there is another important consideration in designing the device architecture, which is also a very important influencing factor, and that is of thermal management. So when any PC RAM cell is designed, specific attention is paid in doing a lot of thermal simulations. What do these thermal simulations tell you? They tell you, when you apply the set pulse or reset pulse, what is the distribution of temperature in the cell, and also what is the dissipation of this temperature, because heat will also dissipate out of this cell into neighboring cells. And as is shown in this particular diagram, you see, in the mushroom cell, most of the heat is getting dissipated into the bottom electrode. Almost 60% of the heat is getting dissipated in the bottom electrode. Whereas in the confined cell, the amount of heat which is going to the bottom electrode, which is a metallic contact, is very less, and most of the heat is actually spreading. Almost 90% of the heat is spreading into neighboring areas. Now, what is the problem if heat spreads into the neighboring areas? It will create a thermal disturb to your neighboring cells, and we will see that the problem of thermal disturb is one of the main reasons why it becomes very difficult to scale the PC RAM. So thermal management is a very important aspect of cell design in PC RAMs. Just a small note, maybe I have missed it. Why is this called a mushroom cell? This is called a mushroom cell is because, as you can see from the simulations and also from this phase change region, the area which gets converted from crystalline to amorphous here looks like a mushroom. Therefore, it is called a mushroom cell. Okay, moving on, let us try to recall why did we go to these two terminal memristor configurations in the first place. We had established DRAM for main memory and NAND flash for main storage. What pushed us to fill this hole into the memory hierarchy? This was the big latency mismatch between DRAM and NAND flash. So the idea of these two terminal passive memristors was to have better bit density than DRAM and much better latency and endurance than NAND flash. So does PC RAM really deliver on this promise? Let us try to examine that. Remember, one of the very important reasons why NAND flash had very good bit density is because of its ability to show multi-bit behavior. It turns out that PC RAM show much better multi-bit behavior. This is because by controlling the amplitude of the set pulse and the duration of the set pulse, you can tune the resistance of this device over orders of magnitude. See, this is log of resistance. So basically, by tuning the amplitude and width of the set pulse, you are able to have different percentages of conversion between amorphous and crystalline phase. So look at this. This is very high resistance. So this is completely amorphous, whereas this is very low resistance. So this is completely crystalline. So between high resistance, which is roughly 10 to the power of 7 to 10 to the power of 3, by controlling different values of the set pulse amplitude and length, you are able to traverse almost 4 orders of magnitude. Therefore, it was shown for the first time by researchers at IBM way back in 2007 that you can have QLC kind of operation. Remember, QLC was quad level cells or 4 bits per physical cell, which shows 16 states. So as you can count over here, there are 16 states spread over almost 3 to 4 orders of magnitude. And what is also remarkable is the spacing between the resistance values of neighboring cells is more or less linear. So this was a wonderful observation by IBM Labs. Furthermore, it was also shown by Samsung just in the next year that the amount of control on variability and the reliability of these cells was also very, very high. And you can really have very tight distribution between neighboring states by using your old technique of program and verify. You do not even need to use ISPP as was used in NAND flash. Just by having write and verify or program and verify, after every programming pulse, you are verifying whether you are reaching your target resistance value or not. You can have a very tight distribution. So as you can see, this open symbol is for the same state without any write and verify, whereas this close symbols, which is a very straight line showing that the distribution is very, very tight, is with write and verify methodology. Not only this, researchers at Samsung also showed that the endurance level of these multi-level PC RAM cells is much, much better than NAND flash MLCs. So remember, NAND flash MLCs endurance was hardly 10 to the power of 4 or 10 to the power of 5 cycles. But as you can see, the endurance of an MLC 2-bit PC RAM cell is almost 3 to 4 orders of magnitude higher than compared to NAND flash MLC. So a natural question which will come to your mind is, if indeed PC RAM is so much better than NAND flash, why hasn't it been able to completely replace NAND flash? Why do we still get solid state drives with NAND flash and not PC RAMs? And this is a very interesting story about the bottlenecks or the challenges that we face in scaling, reducing the device dimensions of PC RAM. The first scaling challenge is something that we briefly alluded to a few slides back. That is regarding the thermal crosstalk. Now remember, crosstalk is a very common phenomena as we keep scaling different memory devices. In DRAM, we saw something called the row hammer effect, and also we saw capacitive coupling in the floating gates of your NAND flash. However, since the PC RAM is inherently a thermally driven memory, thermal crosstalk plays a very, very crucial role in deciding how close you can pack cells. Let me explain with this example. In this particular simulation, what has been shown is cell 1 which has been programmed. So there is a large amount of heat which is generated because of this reset pulse. As you can see, this heat or the temperature gradient has now spread out to the second cell also. And because this spread out in the second cell is so large, it reaches temperatures which could be close to the recrystallization temperature of this particular material. That means if cell 2 is in high resistance state or it is in amorphous state, the spread out of the heat can crystallize some of the material which is belonging to cell 2 as well. And this becomes a big problem in making sure how close you can bring cell 1 and cell 2 together. And this limits the area scalability of PC RAM. However, the second more important or bigger bottleneck is the problem of forcefully having to use something called the access transistor. Now, remember, the promise of two-terminal memristors was to have memory behavior just with two terminals and an active functional layer. So where is this transistor coming from? As we will see even later on in our study of RRAMs, generally all these memristive devices are integrated in the so-called 1T1R, one transistor, one resistor configuration for large scale integration. So here I have shown you the 1T1R implementation in the case of PC RAM. So this is your PC RAM, which is 1R, and 1T is your access transistor. Let us look at this architecture carefully. So the source of your access transistor is connected to the bit line, whereas the drain of the access transistor is connected to the bottom electrode of your PC RAM. Furthermore, the word line of the cell is connected to the gate of the transistor. Now you may ask, why do we need these access transistors? Remember, we have to supply large reset currents. That is what was one of the bottlenecks in the PC RAM technology, because PC RAM technology is essentially driven by thermal Joule heating. Now, if we want to supply a large amount of reset current, the access transistor which is going to supply this current to this PC RAM cell also needs to become large. As we know, larger is the current drivability requirement, larger should be the area of your access transistor. And this is very, very evident in this particular diagram, which is a cross-sectional transmission electron microscope of your PC RAM, which is integrated in 1T 1R configuration. As you can see, the actual GST material contact with the bottom electrode is very, very tiny. However, most of the cell area is consumed by these front end of the line transistors whose drain is connected to the bottom electrode contact, and this side will be connected to the bit line. So the actual programmable volume is very small, but most of the area is being consumed by your access transistor, and therefore area scalability of PC RAMs is a big headache. It is around 20 to 40 F squared. Now this is really, really poor even compared to DRAM. And this becomes the major problem when you try to commercialize PC RAMs. So the commercialization story of PC RAMs is more like a bitter-sweet story, because PC RAM is such a fascinating technology with very high endurance and ability to show bit scaling. Lot of the commercial companies who play in the memory market wanted to commercialize PC RAM, bring it out for consumer market. But if you look at its commercialization story, the picture is slightly different. So let us start with Samsung's effort of trying to commercialize PC RAM. So their 512 megabyte product, just megabyte, 512 megabyte product is something they announced as a replacement for DRAM long back in 2006, and they kept making new announcements that we are going to commercialize in 2009, but the final chip came out much later, only in 2010. Same is the story with Numonyx. Now Numonyx was a joint venture between Intel and ST Microelectronics, and later on it was acquired by Micron Technologies. Numonyx announced that they will be able to go to 1 GB in 45 nanometer node. Remember, 45 nanometer is not your smallest feature size, but it is the dimensions of your access transistor. However, when finally products started coming out in 2010, it was called the Omnio series, and this Omnio series was only able to accommodate 128 megabytes or at max 512 megabytes at 90 nanometer node, a few nodes higher than what was actually promised. So all of this is indicating to one thing, that maybe when you start integrating PC RAMs in large scale chips, maybe the device yield that you get is not as good, or maybe the cost is not very favorable. But the starkest story comes from the joint collaboration between Intel and Micron. Now, Intel and Micron came up with this 3D XPoint memory. So the XPoint was a way to indicate that you have these memoristive elements at a cross point. And these memoristive elements at cross point, just like 3D NAND flash, is also integrated in 3D. Not only that, Intel spent a lot of time and effort trying to integrate this 3D XPoint memory with their Neon processors as a substitution for DRAM. And indeed, they were able to show that their XPoint memory and the Optane processors are much faster compared to your NAND flash, almost 3 orders of magnitude faster than NAND flash. They had almost 3 orders of magnitude higher endurance than NAND flash, and they were even much denser as compared to your DRAM. However, soon after commercialization began from 2017 to 19 with a lot of marketing about the products, they were quickly discontinued in 2022. Now, we don't know exactly what are the reasons, but our friends from industries make some reasonable guess, and the idea was very simple. It was just too expensive to integrate PC RAMs. Why is this the case? This is because PC RAM use fabrication technology which is completely different from your regular CMOS. That is the first thing. The second thing is area scalability, because you were not able to reduce the dimensions of your individual cell. The cost per bit became a very big issue. Also, we have heard that the yield of PC RAMs was not very good. And finally, the rapid improvements in multi-bit 3D NAND flash technology drove down the cost per bit for producing very high quality and reliable NAND flash. This was the reason why, despite having excellent technology in form of PC RAMs, they were discontinued. So the moral of the story is that commercialization has many different aspects which are apart from technology. Sometimes even cost per bit and reliability plays a very important role in recovering your initial investment. So we know that Intel and Micron suffered a lot of losses because of their focus on PC RAM. But as we have discussed, this is a very high risk business, and we have to take these technological gambles. And I would say it is really brave of Intel and Micron to try it. Sometimes we win and sometimes we lose. So the final thing I want to tell you is, although PC RAMs may not really work out for high bit density to fill the gap between NAND flash and DRAM, that is what it looks like now. But recently, both ST Microelectronics and TSMC are developing chips for niche applications for PC RAM, especially in embedded electronics for automobiles and IoT. So wherever you have a requirement for having very fast non-volatile memory with low power consumption, it looks like PC RAMs could make a comeback. However, even in this segment, PC RAMs are going to face stiff competition from resistive random access memories, which is going to be the topic of our next discussion. Okay, so see you in the next class. Thank you very much for your attention.